Okay, so I know in the last class you saw some mathematics, which was bit, of course, it requires some maturity, but and normally, it is not covered in the undergraduate courses. Sometimes they skip in the first course, especially. But anyway, uh, but I have shown you a few things. Today I'm going to start another very interesting thing, which is discrete log. So, you know, if we take a number alpha, raise it to power x, and suppose it is equal to beta, so we know that x is nothing but log of, we can compute in terms of log the value, right? But what happens if alpha and beta are in a discrete structure? Okay, so for example, they may be member of integer modulo p or integer modulo n, right? Then what is the nature of log? How will you define log? Okay, so essentially the definition is same, that we want to find the value of x such that alpha raised to power x is equal to beta. Okay, where alpha and beta are say in integer modulo p. Okay, so how do we compute this? Why this problem is very difficult? You will see that, and it is because of this difficulty finding x given alpha is given the condition that alpha raised to power x is equal to beta. Okay, finding x is a very difficult problem, and that's why people have developed crypto system based on this simple problem. Okay, alpha raised to power x is equal to beta. Okay, so initially I'll talk about the specific case, like we look at integer modulo p or something, but in general you can talk about if alpha and beta are members of the group G. There is a group, okay, having those four conditions, and you can also do everything there. Okay, so so let me look at specific examples, and today I'm going to talk about two algorithms which are often used to compute this discrete log. Okay, so so these are really very beautiful ideas how to actually compute this. So the problem is very simple. I hope you understood that if alpha is for x equal to beta is given, where alpha and beta are members of say integer modulo p, how to find x? Okay, so alpha into alpha x time is equal to beta. You have to find x. Okay, so that is the idea. So let us start. Okay, so for simplicity, I am assuming a simple thing. Suppose p is a prime. Okay, and alpha and beta, here beta is non-zero, are integers modulo p. So basically they belongs to integer modulo p. And suppose beta is nothing but alpha raised to power x mod p. Right. This is the thing. So we need to find x. Right. So normally, if you are on reals or whatever, so we know that how to define log, right? And of course, if you go to the complex plane, defining log is again, you know it's a multi-valued functions, right? And then you can look at the one branch and so on and so forth, right? So there also people defined. So in the discrete structure, what will happen to the log definition? Okay, that is the important thing. Okay, so beta is equal to alpha raised per x mod p is given. I need to find x. So problem of finding x is known as discrete log problem, DLP. Okay, discrete log problem. Okay, so we denote it obviously, so we can define the definition. X is nothing but we call it discrete log. Base of the log is alpha. Base of the log is alpha, right? Discrete log of beta, base alpha is x, right? By definition, it's just same analogy with the reals and whatever, right? We define it like this. So let us take an example. Suppose P is equal to 11, alpha is equal to 2. Okay. Now, what is the value of 2 raised to power 6? We know that modulo 11, this value is 9. So we can write down L2 of 9 is equal to 6. Okay. So one question that I'm going to ask, what is the value of this? Can anyone tell me? 2 raised to power 16 mod 11 is how much? So we know that 2 raised to power 6. So this x is 6 here. 2 raised to power 6 is 9 modulo 11. So that means discrete log of 9 base 2 is 6. Correct? That's my definition. But what if we take 2 raised to power 16? It turns out that 2 raised to power 16 modulo 11 is also 9. And so on. So, which value should we take then in that case? So we take the smallest one. Okay. So the smallest one is our. So 2 raised to power 16 is, so basically I should say that 2 raised to power 6 is same thing as 2 raised to power 16, same thing as 2 raised to power 26, 9 mod 11. These are some different values. So basically we take the smallest. Okay. So now let me recall another idea which we have talked earlier, which is about primitive element. Do you know about primitive element? Primitive element is so for example in integer modulo p, if alpha is a primitive element, so order of alpha is p minus 1, right? Just one less than that, right? Which can generate the whole thing, right? So order of alpha is p minus 1. So often we take here alpha as a primitive element. So that is the, another. So we say that. So actually in that case what happens, because see, if alpha is a primitive element, so beta is normally element of the whole field, right? So basically it will be some power of alpha, right? So the problem becomes a little bit easy to handle actually, right? So if alpha is a primitive element, right? So we often take this condition here. So often we take alpha is a primitive root or primitive element mod p. Okay. So every beta is a power of alpha. So if alpha is not primitive element, then the discrete log may not be defined for certain values, right? So this is our, assumption like alpha is a primitive element, so it's kind of well defined. Okay. So okay, so then you can verify if alpha is a primitive root mod p, then this discrete log of product of two numbers is same thing as mod. Okay, obviously p minus 1 here. Okay, so discrete log of, so assumption is alpha is a primitive element, so order of alpha is p minus 1. That is a condition. So it behaves like normal definition of log, right? Log of product of two numbers is same thing as. So I think you can try to prove this easy fact. So I leave it as to you. It's not very difficult to prove this fact. And actually, so the question is how do we? So question is how do we find this discrete log? Okay, and that is a challenging thing. If p is small, by exhaustive search, actually we can find this value, right? In general, how to handle this? So I'm now going to tell you two algorithms which are very popular for finding discrete log. Okay, So if you are having interest in the complexity, you can actually look at how difficult it is to find the discrete log. But I think I'm not going to do any complexity business. But at least I'll tell you how this algorithm works. Okay. See, one intuitive idea. I mean, just think about it. So beta is equal to alpha raised for x. I have to find x. How do we do that? How to find x? See, one way could be because everything is finite. So what we can do? Take alpha, raise it to some power, and see if it equal to beta. Right? Some random another power, and see if those kind of thinking will evolve into a precise algorithm, which I am going to show you. So I'm going to explain the idea here, how to compute discrete log. Obviously, alpha is a primitive element mod p. So order of alpha is equal to p minus 1. This assumption is there. So it is given to us that beta is equal to alpha raised for x. And obviously, x lies between 0 and p minus 1. Question is find x. Now I'm going to do some. If you look at this expression, alpha raised to power p minus 1 by 2 whole square. What is this value? Alpha raised to power p minus 1 by 2 whole square. So this will be alpha raised to power p minus 1. Order of alpha is p minus 1, so this value will be 1, right? So which is really straightforward. So this value is alpha raised to power p minus 1, which is equal to 1 mod p. Okay. So therefore, alpha raised to power p minus 1 by 2 congruent to, we take the square root on both sides, so it is plus minus 1 mod p. So this value in the bracket, if this whole expression is 1, so that means this could be plus 1 or minus 1, right? Both will happen. That means alpha raised to power p minus 1 by 2 is either plus 1 or minus 1 mod p. Now, since so we observe this fact, but we know that p minus 1 is the smallest because order of alpha is p minus 1. P minus 1 is the smallest integer for which alpha raised to power p minus 1 is equal to 1. So therefore, alpha raised to power p minus 1 by 2 is certainly minus 1 mod p. Okay, so this is our result. Now I'm going to use this fact. Okay, so now we look at beta is equal to alpha raised to power x. Okay, so beta is equal to alpha raised to power x mod p. Just compute beta raised to power p minus 1 by 2 and see what happens. This value will be alpha raised to power. I can substitute the value of beta here, x times p minus 1 by 2. So which is nothing but alpha raised to power p minus 1 by 2 raised to power x, right? Now alpha raised to power p minus 1 by 2 is minus 1. From here, alpha raised to power p minus 1 by 2 is minus 1. So this value will be nothing but minus 1 raised to power x. Everything is mod p, which is there. So beta raised to power p minus 1 by 2 is equal to minus 1 raised to power x. That means this value is either plus 1 or minus 1 depending on whether x is even or odd. At least we got this much information. Okay, so therefore if beta raised to power p minus 1 by 2 plus 1. So basically, if this quantity is plus 1, if this quantity is plus 1, we know that x is even. And if this quantity is minus 1, we know that x is odd. So basically, beta is equal to alpha raised to power x is given. I just compute beta raised to power p minus 1 by 2 and see if it is plus 1 or minus 1. If it is plus 1, for sure x must be even. We've got some information about x. Otherwise, x is odd, right? So once we are given beta is equal to alpha raised to power x, just raise it to p minus 1 by 2 and see what, okay, whether it is plus 1 or minus 1. So this much information is known to you. So in fact, sometimes this information is quite useful. For example, if you suppose 2 raised to power x congruent to 9 mod 11, I have to find what is the value of x, right? Now, since beta raised to power p minus 1 by 2 is equal to 9 raised to power 5, which is same thing as 1 mod 11, I can compute this value, right? That means x must be even. Right. So when x must be even, so I can try x equal to 2, 4, see which one will hit. And you can see that x equal to 6 is going to do the job for us. Remember, we just saw this example. 2 raised to power 6 is congruent to 9 mod 11, right? So start from, so we got some information, so our search space is now limited, right? So go for x equal to, 2, 4. Which one is the smallest one which will hit the thing? You know the answer, right? So that is how you can calculate this discrete log. So here basically x is equal to 6. Okay. Now, any other ideas do you have in your mind? So if I have to compute this, I mean, what you are thinking as a fresh mind. So we are given beta is equal to alpha raised to power x. How do you compute x? Any idea from your side? Because simple ideas sometimes lead to a good algorithm also. So anything that you have in your mind, how do we compute? So okay. Anyway, so I'm going to give you the first algorithm, which is, now you see, I'll assume certain form for x and try to find the value. So let us see. So this algorithm is known as Polig-Hellman algorithm. Okay. Now there are certain, again, assumptions. See, basically in general finding the problem is difficult. So what we are going to do, again I'll put some assumption. Okay. So for example, in the last slide you saw that if we compute beta raised to power p minus 1 by 2, if it is plus 1 or minus 1, I can guess whether it is even or odd, so such space is reduced. That is one thing. So here I'm going to assume that let p minus 1, p is a prime, right? You remember, let p minus 1 is partial product of these prime factors. Suppose p minus 1 is equal to partial product of qi raised to power ri. This is a prime factor, right? P minus 1 will be integer. Obviously, we can have some prime factor, right? Now, so I mean, this is a typical for any index. In general, a prime factor. So that means a prime factor q raised to power r will divide p minus 1, right? So we are actually working to compute discrete log of beta with base alpha modulo q raised to power r is prime factor. Okay. So this is our thing. So now, so you remember the problem is what? So we are given that uh, beta is equal to alpha raised for x. This is given to us, right? I mean, and I have to find x. I assume that x is something like this: x naught plus x1q plus x2q square and so on. Keep on doing, sorry. X is equal to x naught plus x1q, x is equal to x naught plus x1q plus x2q square, and keep on going to each xi between 0 and q minus 1. Suppose x has this kind of expansion. Then I can compute x mod q raised to power r, because now we are working on this system, right? So we are computing discrete log with respect to mod of qr, q raised to power r, right? So what I'm going to do, x is something like this, our assumption. Now I'll compute what is this value, mod q raised to power r. You will see that the expression is a little bit simple, and that can be used to compute the value. So that means x times p minus 1 by q. P minus 1 by q will be what? X naught times p minus 1 by q plus p minus 1 times x1 plus x2q and so on, right? This is plus actually. The whole thing can be, so I'm just computing this value. So x is given here. I'm just computing x times p minus 1 by q can be written like this: x naught, the first term, times p minus 1 by q plus some integer. So I call this, because this is an integer, because you know xi's are between 0 and q minus 1. So this will be some integer. I'll call it n. Okay, some integer. I'll call it n. So the whole expression is, we have so I can write down the whole thing as x naught times p minus 1 by q plus n. I mean, this is very bad actually, you know, here. Whole thing is x naught p minus 1 by q plus n. Okay, so the whole thing is some integer n. The right hand side is some integer, right? So this expression is I'm going to use actually. See, this is the important thing. Okay, so now, so x is x naught times p minus 1 by q plus n. Now I'll attack the problem. So beta is alpha raised for x. I have to find x. What I'm going to do this time, I'll raise beta raised for p minus 1 by q and see what happens. Earlier you saw that we raised beta raised power p minus 1 by 2. Now it is p minus 1 by q. Okay, and then this value will be alpha raised power x times p minus 1 by q. I just substitute the value of beta, and so this can be written as alpha raised power x naught p minus 1 by q into alpha raised power p minus 1 raised to power n. Any idea what is this value? Since order of alpha is p minus 1, so this value will be 1 anyway. So we are left with alpha raised power x naught times p minus 1 by q, right? So that is okay. So this whole thing is nothing but x raised to power, sorry, alpha raised power x naught times p minus 1 by q. Okay. So I need to basically now find the value of c. In the expression, x is unknown. So now we are left with x naught is unknown, right? X naught is unknown to us. So what I am going to do? To find x naught, we look at powers of alpha as k times p minus alpha raised to power k times p minus 1 by q. K is 0, 1, 2 up to q minus 1. what I'm going to do, so I'm going to look at this power. So because x naught, I don't know which is going to work, right? So what I'm going to do, I'm actually just computing this for different values of k and see which one is equal to beta raised to power that, right? So that way we can actually solve. So you can see the approach. We are trying to reduce the search space all the time, right? By putting different conditions, can I simplify the problem? Okay, that is what actually we are going to look at. So, so we are just raising this power for different k until we find uh, that this value is, for some k obviously, it will be equal to beta raised to power p minus 1 by q for some k, right? In that case, obviously, x naught is nothing but that particular k. Okay. So this is how we are able to find, you know, the first term. So basically, in the expression, here we had x is equal to x naught plus x1 q plus x2 q square and so on. I'm able to find x naught till now, right? Only one thing, one term in this unknown. Now I need to find x1, then x2 and x3 and so on. So how do we do that? I'm going to again use the similar technique to find x1 and again repeat the similar technique to find x2 and so on. Okay. So you see that whatever procedure I have done for x naught, I'm going to do it for x1 also. So here is the thing. So here, okay, so now what I'm going to do, assume that q square divides p minus 1. We are looking at the next power and assume that beta 1 is equal to beta times alpha raised to power minus x naught, beta times alpha raised to power minus x naught, which is alpha raised to power q times x1 plus x2q and so on mod p. So then we compute beta 1 raised to power p minus 1 by q square. This is nothing but, I can again simplify. The technique is exactly similar. This time I am looking at different coefficients by q. So this is nothing but alpha raised to power x1 p minus 1 by q, and rest of things will be actually alpha raised to power p minus 1 whole raised to power x2 plus x3q and so on, which is the integer. I mean, this value will be 1 anyway, so we are simplified. We are left with alpha raised to power x1 times p minus 1 by q. Okay. Now again, to find x1, x1 is unknown here. So we actually try different powers. So alpha raised to power k times p minus 1 by q, such that this is equal to the first term. Okay. Once we find k, I mean, we know the value of x2. So basically, to find x1, what I'm going to do, I look at alpha raised to power k times p minus 1 by q mod p. So k is equal to 0, 1 up to q minus 1, and see which one is equal to beta 1 raised to power p minus 1 divide beta 1 raised to power p minus 1 divided by q square. Okay. So the left hand side actually, you see, right? So whenever we find a key k, right? So in that case, that k will work as for x1. So we know the value of x1. So basically, this is the approach we keep on doing until we find, you know, So we find x naught, x1. So next time we will try q cube divides p minus 1 for the next step for x3, right? And so on. Same thing we repeat. So we find x1, x2, xr minus 1. So we know so when we have all the values mod q raised to power r, so we know we get the value of x. Okay. So basically, what we get x modulo q raised to power I ri. Now, so I hope let me just repeat it here. So our approach was we assume that p minus 1 is product of these prime factors. Then what we are going to do for each modulo qi raised to power ri. So basically for each of them, right? I'm going to do. So basically I'm looking at, say, one typical scenario is q raised to power r. So for some I am so simplifying the writing is that q raised to power I is a factor of p minus 1, right? So initially we tried the smaller case, right? And then we write x like this, and our job is to find this x1, x2, x, x3, x4 up to xr minus 1. So what I'm going to do, we have computed this technique. We found x naught. We similarly find x1, x2, and so on. And finally, so we find all these values. Each of these values we find modulo q raised to power r. So by the combination, that means we find the value of x modulo qi raised to power ri. Now your friend Chinese remainder theorem can be used because this is the product of these things is nothing but p minus 1, right? So using the Chinese remainder theorem, I can find x modulo p minus 1. So we have got the answer, right? I hope you understood the thing. Such a typical thing is to first find x1, x0, x1, x2, and there also we are just raising it to power and see which one is equal in that approach all the time, right? And once we collected these x0, x1, x2, x3, and so on, right? Then we are going to compute x by taking combination, but that x we know modulo qi raised to power ri, right? For each I. And then using Chinese remainder theorem, we can find x modulo p minus 1. Okay. So let me give you an example here. P is equal to 41, alpha is equal to 7, and beta is equal to 12. I need to find this is very bad. I'm not sure, or I don't know how to write it yet. So I have to find x. So anyone tell me what should we do now? So we are given the problem is very simple. P is equal to 41, alpha is equal to 7, and beta is equal to 12. What we should do? You just saw the algorithm. First of all, I need to look at the factorization, right? Which is 41 minus 1, which is 40. Write down as a prime factor. For each prime factor, compute those values, right? And then let me show you. By the way, if you have found your own algorithm, please let me know, over a cup of tea if you can find, because the problem is very simple, right? You have to find x. So we note that 41 minus 1 is equal to 40 is equal to 2 cube into 5, right? So I need to look at one case, modulo 2 cube. I have to look at another case, modulo 5. Then I will apply Chinese remainder theorem, right? So I need to find x modulo 2 cube. I need to find x modulo 5. And then apply Chinese remainder theorem to find x modulo 40. Got it? Okay. Now let q is equal to 2. I mean, here actually. So what we can do, we are going to find x modulo 2 cube. Okay. We can write down x as x naught plus 2x1 plus 4x2 mod 8 To start, beta raised to power p minus 1 by 2 is nothing but beta raised to power p minus 1 by 2 is nothing but 12 raised to power 20 is nothing but 40, nothing but minus 1 mod 41. Okay, we have got this value, and I can look at alpha raised to power p minus 1 by 2, alpha raised to power p minus 1 by 2, 7 raised to power 20, congruent to minus 1 mod 41, right? Since beta raised to power p minus 1 by 2 is same thing as alpha raised to power p minus 1 by 2 raised to power x naught mod 41, what I can do here now, this implies that which power will it be? X naught is equal to 1, right? Next, beta 1 is equal to beta times alpha raised to power minus x naught. I'm just executing the algorithm steps, is equal to 31 mod 41. Now beta 1 raised to power p minus 1 by 2 square is equal to 31 raised to power 10 is equal to 1 mod 41. Okay, so since beta 1 raised to power p minus 1 by 2 square is congruent to alpha raised to power p minus 1 by 2 whole raised to power x1 mod 41. So x1 is equal to 0. Continuing this way, actually we arrive at beta 2. So I will leave few steps, just verify that x2 is equal to 1. So x is equal to x naught plus 2x1 plus 4x2 turns out to be 1 plus 4 is equal to 5 mod 8. Okay. So next is when now we are, so basically we had two things here, right? 2 cube and 5. So 2 cube we have taken q is equal to 2. Now I have to take q is equal to 5. So when q is equal to 5, so I need to find x mod 5. So again beta raised to power p minus 1 by 5. This will be 12 raised to power 8, 18 mod 41. So and alpha raised to power p minus 1 by q is equal to 7 raised to power 8 is equal to 37 mod 41. Trying different values of k, you will see that, so 37 raised to power 0 is 1, 37 raised to power 1 is 37, 37 square is equal to 16, 37 cube is equal to 18, 37 raised to power 4 is equal to 10. All mod 41 we are computing. So that means this, because this is 18, so this value is going to work here, right? So x is congruent to 3 mod 5. So one value is x is congruent to 3 mod 5, another value is x is congruent to 5 mod 8. Right. So we have got two values. So we have got one value as x is congruent to 5 mod 8. Another value is x is congruent to 3 mod 5. By Chinese remainder theorem, x is congruent to 13 mod 40 using CRT. Therefore, 7 raised to power 13 is equal to 12 mod 41. So, such a lengthy step, but it works actually, at least, you know. Okay. So this is just one approach. So basically now x is equal to 13, that means here in this case, right? So So I think I'm going to tell you one other method which is known as index calculus method. How many of you are reading the book? कोई पढ़ रहा है? कोई नहीं पढ़ रहा होगा नहीं? Okay. Let me do one thing. When is the next class? Friday, right? Friday है ना? नहीं है? साइन अप तो आफ्टरनून में होता है ना? So I love these things. You know, when there is something going on, you take a quiz, right? Anyway, I'm going to do one thing. Read index calculus method. It's not very difficult. And read index calculus method from the book, and let me see what you can do. Right. If it is not on the Friday, we can do whatever the next day. You know, read index calculus method. I mean, I want you to read the book at least, right? Index calculus method. Understood? What is index calculus method? Okay, just read it. Again, it will do some sort of these kind of, along the same lines, assume something like this and see if it happens and so on and so forth and try to calculate, right? Read it. It's very important because you may come up with new ideas which are very, very more, but this is a very difficult problem, right? Can you find a different method of solving it, right? So read about the index calculus method, and we will see in the next class whenever it is. I'm not sure if it is Friday or the next. Okay.